All right, so to conclude our lecture on section 6.6, I just want to do additional exercises and examples involving parameterized surfaces, the surface area, the surface integrals, and flux. Okay, so here's the first example. I go back to the coffee filter, which is the top half of the double cone. And so this cone is parameterized by the standard one that I gave you earlier, u cosine v, u sine v, and u, as u goes from 0 to 1. So z goes from 0 to 1, because that's what u is. And then v goes from 0 to 2 pi. That will give you around the entire dripper, right? Okay, so if you are to find the area, okay, what is the area, right? The area is, you may want to write down what you need first. The area is defined as this, right? It's a double integral of ds, but in order to calculate this, we actually use RU cross RV, and then we find the norm of it, and then you integrate it over this region, domain D, defined by the upper and lower limits of u and v, right? So whatever you do, you're going to have to find RU and RV. Okay, and that's probably true for like all surface integrals. So you may as well just find RU and RV for every surface integral problem, okay? And that's why I'm saying this becomes automatic once you start to do these problems. RU is cosine V, sine V, and 1, right? That's RU, by the way. And RV is negative U sine V, U cosine V, 0. And then RU cross RV has to be evaluated, and that's 0 minus U cosine V. Right, and the next one will be negative U sine V minus 0. Last one is tricky. Okay, what the last one is this times this minus this times this. I'm not going to write down all the details, but if I read this calculation, this will be u cosine square v minus negative u sine square v, which becomes u cosine square v plus u sine square v. Okay, did you get that? It's basically just u. Okay, and there's only one u because the top row RU does not have any u in it. So this is, that's pretty nice. Okay, that's your cross product. And so for this, the area, you need the absolute value or the norm of it. And so you can go ahead and calculate this. This is u square cosine square v plus u square sine square v. You've seen this many times. It's a square root of u square. So this will be plus or minus u, except u is always non-negative in our domain. So this can be just written as u, okay? Now the area is easy. Area is the double integral, and then you can go from 0 to 2 pi, and then 0 to 1. And then we just found out the magnitude of the cross product is u, and then you have du dv. All right, and so this will be from 0 to 2 pi, and then you have u square over 2 going from 0 to 1. All right, so that is 1/2 times 2 pi, and the answer is just pi, and that is the area of this cone. Okay, so that's not too bad. Number 2, if the density of this surface S is rho is the square root of z, okay, find the mass. Okay, how heavy is, this S, right? Now remember, this time you have to find the mass, which is basically the surface integral, where you integrate rho. Okay, this is what you have to do. Right, so basically you just have to have rho right inside, insert that here. Right, that's all you have to do. You already have RU cross RV and the magnitude of it, right? So let's write rho. Okay, so what you have to observe is that rho is the square root of z. Well, z happens to be, where is my z? Z is u, okay? So it's a square root of u, okay? That's what I need to integrate. So this is going to be very similar to what we just did. From 0 to 2 pi from 0 to 1. And then you have this rho, the density function, which is the square root of u. And then everything else is the same. You have to still have, you have to have all of these. So it's u, du, dv. Okay, like I said, it's very similar to the one on top, but this time you will not just get the area, but you will find the density. And by the way, as you know, it's a square root of z, right? So as you go up, as z increases, it gets heavier and heavier. So the top part of this um, of surface S is made of a heavier thing than the bottom part. That's the picture you have. Now, what is this thing here? This is u to the 3/2, right? All right, so then our integral will change slightly. The first part will be, what is that? 2 over 5 of u 5/2, right? And then going from 0 to 1 dv. Okay, so I must be really tired. I apologize, but I need to stop and change something here. Maybe you caught this too. Back here, RU cross RV was this, right? And then I forgot because this is so similar to what we had before. But let me go ahead and erase this part here. This is not correct. Why is it not correct? Okay, well, because I forgot, I did this square plus this square. I forgot there's another one. So this will be plus u square here, right? So the first two will add up to u square, and you have another u square. So this is the square root of 2u square. And so this is the square root of 2 times u. Okay, so I apologize for that. And so that's what I need to have for here. This is the square root of 2 times u. That's what you have to integrate. And so I can take the square root outside, square root here, and the answer is not this, but this is equal to square root of 2 times pi. Okay, and again, I apologize for that. That is a bad mistake. And sometimes when you are in a hurry, you make a mistake like this. I hope you notice that and they say, hey, what's wrong with this? You know. All right, the density, rho is the square root of z. And again, I have to have, what do I have to have? Rho is a square, this part is okay, right? And then I just have to make a little change here because you have the square root of 2 times u over here. All right, so that changes the mass also because I have to insert, you know, square root of 2 times u is my, the norm of RU cross RV. So I have to enter this one as well as this. So this part goes here, and the square root of 2 times u is my the norm of the cross product, right? So let me move the square root of 2 in the front at each of these places. I still have u times u to the power of 3/2 to integrate, and that becomes 2/5 times u to the 5/2, right? All right, so then we go on. This is the square root of 2 times the integral of from 0 to 2 pi of, and this is just 2/5 dv. All right, so this is 2 square root of 2 times 5 divided by 5, and then you have 2 pi. So this is 4 square root of 2 pi over 5, and that is the mass of this object. Okay, using the same surface S, which is the coffee dripper we were talking about, let's say this is actually a filter, you know, and then things are penetrating, things are going through, going down. And so I'm going to define this vector field F, which is 0, 0, u. So from here, it's just coming down like this. And as you go down here, it's getting smaller and smaller. And right at this point, there's nothing going on, right? Maybe because this is just an apex and so on, right? So u, remember, was z. So this point, actually, it's minus, okay, minus u. This is my vector field. So it is kind of going down, 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 and so on. Things are penetrating, and the question is, how much of this fluid, coffee, is going down from the top to the bottom of this filter? All right. So that's the question. Basically, I really should be writing this in terms of z, x, y, z. So let me correct that. So the question can be phrased like this: if f is negative, if f is 0, 0, negative z, which is described by this picture here, then find the flux, right? And so you remember the flux, and the first time you do this, you may want to write this down, because this is what you're trying to find, right? This is the definition of the flux. But what we found is that this is, it can be done without finding the magnitude of RU cross RV. What you do is find the RU cross RV and then dot that with F, and then you integrate on on the UV plane. So what we have to calculate is that particular part. Okay, so what we are doing is, remember RU cross RV. In our case, RU cross RV was negative U cosine V, negative U sine V U. Now, how do you know that? Well, because we already calculated that, right? Instead of going this far, we stop right here, okay? And so you write down that three-dimensional vector. That's what this is, okay? And then the next thing is, instead of finding the norm of this, we say, well, F is 0, 0, and negative Z can be written as negative U, okay? Because that's what, that's what this was. And by the way, if you are to graph this, remember U is Z value, right? So this will be, it'll be the one that has the Z value going up. So this will be the vector that goes like this, okay? That is the normal direction right now. So remember, what we're trying to find is the opposite direction, okay? So if you calculate this, I bet the answer is going to be negative. I hope you understand what I'm talking about. See, we're trying to find the flux of this filter or the coffee going from top to the bottom of the filter. But what we have is the normal direction, the orientation of the normal vector, which is calculated by RU cross RV, has the Z value positive, which means that it is perpendicular at every single point, going from the bottom of this side to the inside of the filter. So our answer is going to be negative. So we have to change the negative sign to a positive sign when you find the flux. All right. Anyway, F is 0, 0, negative Z, which is 0, 0, negative U. Okay. Now we can find F dot RU cross RV. If you remember back in chapter 2, which is the very first chapter we studied in calculus 3, I told you that you should remember dot product and cross product, because these will be haunting you if you don't understand this, right? So here, many weeks later, we are still dealing with the cross product and dot product, even in one aspect, or the one small part of a big problem here. Okay, so you take the cross product, you dot that with F, and you get negative U squared. Okay, that's pretty simple. And so the flux for this will be from 0 to 2 pi, from 0 to 1, and then what you integrate is negative U squared. All right, and that is the whole thing here. And then you have the U dV. Okay. And so now it becomes negative U cubed over 3 going from 0 to 1 dV. And that, of course, is negative 1/3 times 2 pi. It's negative 2 pi over 3. All right. Oriented upward. So that means the downward flux is 2 pi over 3 over this entire filter. Okay, so that's how you can calculate a thing like this. Okay. All right, so the final question here, find the mass of this quarter of a cylinder S. All right, so S has a radius 1, and the length here is 3. This point is 0, 3, 0. And so that's my surface S, and the density function has to be defined, of course, to find the mass. The density is F of X, Y, Z. Remember, the density has to be defined on every point of S, which is a point on the X, Y, Z space. So this is Y plus Z. Okay, actually, I'll tell you what, this is page 299 in the book. It used to be my assignment when I used to use So this used to be an exercise, a homework problem when I used to assign problems from the book. It's not page 299, by the way. Sorry about that. It's a practice or an exercise 299 in the book, right? So if you go to the book, you can find exercise 299 from this chapter, and this is exactly the problem. All right, so well, it actually doesn't say the math. It says find this, okay? And the integral, I mean, the mass we have to find is, what is that? It's a double integral over S of f ds, right? And so that's what we need to find, right? And that is the question in number 299. I'm interpreting this question as the one where you have to find the mass. Okay, so the first thing is you have to parameterize this, okay? So there are many ways to parameterize this maybe, but the easiest way is, remember this circle, you have to have x squared plus z squared, so not y squared, right? Because of the orientation of the cylinder, you have to have x squared plus y squared equal to 1. And then y simply goes from 0 to 3, okay? So what's the best way to do this? Cosine of u, v, sine of u. See, the thing is, x squared and y squared, z squared have to add up to 1. So that means you have to have cosine u and sine u in the x and z coordinates respectively. And then y is going to be independently v. And so I want u to go from 0 to, and because it's a quarter of a circle, pi over 2. Okay. And by the way, I want to make sure this is the right quadrant. Right? It starts at this point because, you know, if u is 0, then you have 1, 0, 1, which is this point. And when u is pi over 2, you end up here, 0, 0, 1. So that is perfect. That is the right thing that I'm looking for. And then v goes from 0 to 3 independently of u, right? And so now what do you have to do? Well, yeah, as always, you have to find RU, RV, RU cross RV, and its magnitude, okay? And then you have to find what the F is, right? So F is Y plus Z, so you may as well write this as V plus sine of U, because that's, you know, this is Y and this is my Z. Okay, RU, it's negative sine U, 0, cosine of U. RV, 0, 1, 0. RU cross RV, negative cosine U and positive sine U. Is that right? No, that's it. That's not it. Its y is actually 0. The second coordinate is 0, right? Because you have 0 here and 0 here. So that would be 0. And then the last component is negative sine of u, okay? And at this point, RU cross RV has the norm, which I think you can tell it's square root of cosine square plus sine square, which is the square root of 1, which is 1. Okay, that's easy. And by the way, just again, just note this. The orientation of this normal vector, yeah, what's the orientation of this normal vector? Well, see, like for instance, when u is equal to 0, okay, when u is equal to 0, you're at right this point, and there it's negative 1, 0, 0. So it's this direction, right? So if you were, and you are not doing this at this point, but if you were calculating the flux, it's actually going from this side over to the opposite side of, of S. That would be the orientation of this normal vector. It would be important to note that if you are calculating the flux, so you know which flux or the orientation that you are taking. Okay, but anyway, so this is my vector, my real valued function f. All right, so the mass can be calculated by, right, so let's go from 0 to pi over 2, and then 0 to 3. It doesn't matter if it's dv du or du dv, because the area, the d, is rectangular. And then you have v plus sine u. That is my function f. And then you multiply this by 1. Well, that's nice. Okay. And then you have dv du in this order because of the upper and lower bounds of my integral, right? So if you integrate with respect to v, you get v over 2 plus v times sine of u, and then you can go from 0 to 3. And so this will give you 9 over 2 plus 3 sine of u, and then this whole thing has to be integrated with respect to u. So it's 9 over 2 u plus 3, actually, sorry, it's negative 3 cosine of u as you go from 0 to pi over 2. And if you evaluate this, this is not a hard problem at this point, right? Yeah, so this part is not too difficult. You just plug in pi over 2 over here. And then, of course, if this is 0, you don't get anything. Negative 3 cosine, it's a little tricky, right? Because cosine of u is cosine of pi over 2 minus cosine of 0. That would be negative 1. And so 3, and then you have 0 minus negative 1. And so this will give you a positive 3. And so if you get the common denominator 4, then you get 9 pi plus 12 all over 4. And this will be the mass of this quarter cylinder. Okay, so I know this has been a very long section, and typically I spend like 2 full days, or 2 full hours for this. And so it's been long, but I hope you have understood the basic concepts here. All right, so let's review just very quickly. We first learned how to parameterize surfaces, right? And then we found how to find the area of the surface. And then we found out how to calculate the surface integral when f, some real valued function, is defined on that surface, right? And then finally, we use that to evaluate the flux of whatever is defined by the vector field f over the surface S, right? And I did some examples. Okay, so make sure you understand this, because the next 2 sections will depend on these concepts. Now, the good news is the next 2 sections, which are the very last 2 sections you will learn in Calculus 3, aren't as long as this one. All right, so just to be prepared to enjoy the last 2 sections of Calculus 3 and your entire calculus sequence. All right, until next time, I hope you have a great week. Take care. Bye.